Hello. Hello?
Hello.
Oh, sorry, it's just me.
Hello. Good morning, everyone. It's 2 minutes past 9. We should definitely start. So please be seated, and we'll wait for a few people. Right. So the first talk of the morning is by Jenny. So Jenny, you have 12 minutes to talk, so should keep some time for questions.
Okay.
So please go ahead. The stage is yours.
Can you hear me? Does this work? Okay. I'll clip it up here. Okay. Before I start, I just want to, thank the organizers for inviting me here and giving me the chance to present my work. This is actually my first conference ever, so that's exciting or terrifying. I don't know. But yeah, my name is Jenny. I am a master's student at the University of Cambridge, but I'll be starting my PhD in the fall at Stanford. And today I want to talk to you about the stochastic modeling of star formation histories, in particular how we can use this in the context of SED modeling, as well as some first observational results I've obtained from this method. So, as we all know, one of the main limiting factors in our current understanding of how galaxies form and evolve is the uncertainty in the physics of star formation and feedback. Because the processes going on in and around a galaxy span so many orders of magnitude in both spatial and temporal scales, it's really a challenge to get a good picture, a good and accurate picture of what's going on, especially since we can only observe a galaxy at a single point throughout its entire lifetime. And so the main question that I am interested in is what can the variability in the star formation histories of galaxies teach us about the physical processes that help to regulate its growth and evolution? Is this variability mainly related to gas physics acting on large scales or to small-scale cloud physics where star formation is actually taking place? In other words, like what timescales are encoded in the scatter of the main sequence? How might this depend on things like stellar mass, cosmic time? And just thinking about some of the things that we've discussed this week, to what extent does this variability in star formation at high redshifts contribute to this observed bright end slope of the UV luminosity function? And so in order to answer these questions, we have to somehow quantify this variability. So if we think about a galaxy's star formation history as a time series that's driven by some set of stochastic processes, we can relate the stochasticity in the star formation rates of galaxies to the physical processes that are going on inside of them using a power spectrum. And so this is exactly what my advisors Sandro Tokela, John Forbes, and Nevin Chapler do with this extended regulator model, which is defined by this power spectrum right here. And so I'm not going to go into all of the technical details here, but really the key ingredients that determine a galaxy's star formation activity in this model are gas inflow into a galaxy, cycling between atomic and molecular gas in equilibrium, and smaller scale dynamical processes, things like the formation and disruption of GMCs. And so each of these processes acts over some characteristic timescale and serves to correlate a galaxy's star formation history over that timescale. And we can quantify this correlation structure with the autocovariance function, or the ACF, which is just the Fourier pair of this power spectrum, or PSD. And so if we look at this equation of the ACF on the slide for the extended regulator model, we can see that there are really two parts. There's this long timescale gas component, which is this first part right here. And this describes the correlation of star formation histories over long timescales. And so the parameters of interest in this part are tau in, tau equilibrium, which are the timescales over which gas inflow and this equilibrium gas cycling are correlated, and then sigma reg, which is the overall level of variability in these gas processes. And then the second part, is describes the shorter scale dynamical component and these shorter-lived star formation correlations. And here, tau din is the characteristic timescale over which these short-term dynamical processes are correlated, and sigma din is that associated level of variability. And so what we expect to see in actual galaxies is for their star formation histories to be rather correlated over short timescales. So they would have large covariance values at these short timescales and low power in these short timescale high-frequency fluctuations. And for star formation histories to decorrelate, or like you would see more variation, as you go to longer and longer timescales, and as they decorrelate. They decorrelate at long timescales, and then you get more power on these long timescale, low-frequency fluctuations. And so we can turn this sort of correlation structure into a star formation history prior that we can use in SED modeling, which is what I'll talk about now. So we focus on the SED modeling code Prospector, which lets you flexibly model galaxy star formation histories by fitting for the star formation rates in these individual time bins. But in order to do this, we have to give Prospector some sort of prior, basically to inform the model of what physical space we expect these star formation histories to lie in, so that it doesn't go off into crazy space. And so Prospector typically does this with the continuity prior, which parameterizes the ratios between adjacent time bins with the student t distribution, or with individual student t distributions. And this serves to sort of weight against any sharp jumps in the star formation history. And this continuity prior typically does a pretty good job of recovering the star formation histories of galaxies, but it's not exactly physical in the sense that it doesn't correlate the star formation rates between these bins. And so, in principle, you could have star formation histories that vary arbitrarily from one bin to the next, which is not what we expect to see in actual galaxies. And so what we do in our stochastic prior is, instead of parameterizing these ratios with individual t distributions, we use one multivariate normal distribution whose covariance matrix is given by this covariance function of the extended regulator model. And so what this lets us do is to correlate the star formation rates between bins based on a physical model for the behavior of these star formation driving processes. And what you see on the slide over there is just an example of what the prior density for this stochastic model to look like. And so the easiest way to use this prior would be to fix the covariance matrix by choosing physically reasonable values for these sigmas and taus, or the PSD parameters. Or you can let them vary in your SED fitting procedure and have your model take on this sort of hierarchical structure, which is what we do. And I just want to clarify here that we are not trying to measure the PSD parameters of individual galaxies, because that would be very, very difficult to do, but instead derive joint constraints on the PSD over an ensemble of galaxies, so that each individual galaxy sort of acts as a probe of different parts of the PSD. The thing is, we can't actually implement a fully Bayesian hierarchical model in Prospector at the moment. So we have to combine the constraints of galaxies after the fact, but it's something that we hope to be able to do in the future. And so before I use this on actual data, I tested our stochastic prior on a bunch of mock observations that I sort of injected with different levels of star formation variability. And what we found was that our stochastic prior did basically at least as good of a job as the continuity prior. We were able to recover key galaxy parameters like stellar mass, which you see up there, to a very high level of accuracy with minimal scatter, minimal bias. And we actually outperformed the continuity prior when it comes to modeling star formation histories, which you can see in this bottom panel, because of this physical variability information that we sort of bake into our model. And then lastly, in terms of the PSD parameters, somewhat unsurprisingly, we found that we aren't really able to constrain most of them, but we can approximate the sigma reg parameter, which is, again, the variability in these long timescale fluctuations over an ensemble of galaxies. And so now it's time to use this on data. So I jointly fit the spectra and photometry of about 1,500 galaxies from the legacy survey. So these are massive intermediate redshift galaxies in prospect or using our stochastic star formation history prior. Here on the slide, you just see an example of one of the galaxies. In my sample, as you can see, the model does a pretty good job matching the data, which is nice. So now we can look at some of the results that I get from all of this SEV fitting. So first, we can take a look at the sigma reg parameter, which is the variability on these long time scales. What you see on the plot here is all of the galaxies in my sample on the SFR mass plane color-coded by sigma reg. And clearly, there's a trend. Galaxies on the main sequence tend to have a low value of sigma regs, less than a dex. And then as you move off of the main sequence into the quiescent population, sigma reg becomes larger and larger. And what this tells us is that the amount of power contained in these long time scale fluctuations is greater in quiescent galaxies than in star-forming ones. And I think this makes a lot of sense because if you think about it, quiescent galaxies have all experienced this sort of general trend in their star formation rates on long time scales as they went from star forming to not star forming. So this tells us something about the relative importance of these long time scales in star forming versus quiescent galaxies. But what about these short time scales? How do they come into the picture? So to investigate this question, what we do is we assume that a galaxy's current position relative to the main sequence is due to a combination of some short time scale offset and some long time scale offset, so delta S and delta L. We define delta L to be the median of its offset from the main sequence measured at a series of lookback times throughout its star formation history up to a gigayear. And then delta S is just the difference between these two values. And so then we can quantify the relative importance between these short timescale fluctuations and long timescale ones by looking at the difference between their absolute values. So if delta S minus delta L is greater than 0, then a galaxy's position relative to the main sequence is primarily due to these short timescale fluctuations, short timescale processes. But on the other hand, if it's less than 0, then long timescale processes are more important. And so when we look at these values for galaxies across the sample, this is what we see. So in quiescent galaxies, we find that delta S minus delta L is negative, which tells us that long timescale processes are more important to this continued suppression of star formation in quiescent galaxies. And this also sort of supports the large sigma regs that we found 2 slides ago. And then when we look at galaxies on the main sequence, we see that delta S minus delta L is approximately 0, which tells us that long and short timescale processes play approximately equal roles in regulating the star formation activity on the main sequence. And so short-term variations might be associated with things like the self-regulation of star formation, and these longer timescale variations might reflect more of these environmental processes. And this is also supported by what we see when we measure the scatter of the main sequence averaged over different timescales. And so sort of making a similar assumption as before, that the scatter of the main sequence is due to the scatter from short timescale variations plus the scatter from long timescale ones. When we decompose the main sequence scatter in this way, we find most clearly in lower mass galaxies that this sigma L and sigma S are both approximately 0.2 dex, which tells us that fluctuations due to long timescale and short timescale processes contribute more or less equally to the scatter of the main sequence that we observed. And so this brings me to my conclusions. And the one thing that I will say is that I think the stochastic star formation history model could potentially be a powerful tool for the high redshift universe and measuring the star formation histories of these high Z galaxies. And it could potentially tell us something, help us learn about the role that these bursty star formation play in these high Z systems. Thank you.
Thank you. Questions? Okay.
Hi, thank you for your talk. Can you explain again why you think that for quiescent galaxies is the long-term modes that are dominating? Because I would expect just the opposite, because a quiescent galaxy must have had some, maybe a series of bursts that eventually quench the galaxy.
Yeah, I think part of it is because like we found that the quiescent galaxies in our sample quenched probably like over a gigayear ago. And so it's harder to measure the star formation history at large look-back time. So, you know, you like sort of get rid of these shorter-term fluctuations at the very beginning because you just can't really.
Okay,
and
that's
so all
good.
you see is this long-term, like, star forming.
Yeah, because nothing happens internally at
Yeah,
that point, right?
yeah.
Okay, thank you.
So while we take the next question, maybe Mike, you can set up.
Thank you. I was wondering, sorry, two questions.
Yeah.
What's the limit on how short you can make the bursts in your model? And secondly, do you find that there are any degeneracies between like the duty cycle you choose and other parameters in your modeling?
There is a degeneracy, like in this model in specific, there's a degeneracy between like tau equilibrium and this long time scale fluctuation. It's easier to, I could show you later, but like, you know, depending on like what values those are, they can produce the same power spectrum. So that's a thing, but this sigma tends to have a much bigger effect on what your like star formation prior looks like. So that's the one that you can really measure. But then there are the uncertainties that come in from whatever value of tau you choose.
I guess we have enough time. Very nice talk. So, you know, in this kind of statistical model where you're generating randomized fluctuations in the star formation history, I'm wondering, is it possible for you to do model selection in this model compared to something that's simpler? What are the distinctive features in the end that can be reproduced only in this kind of statistical fluctuation model that cannot be accounted for in another model, and how can you, you know, tell them apart in the end? Is there anything really unique about this model that can't be achieved otherwise?
Yeah, you know, I'm not totally sure, but like I think one of the big selling points of this model is that we do find that we can like reproduce star formation histories more accurately than like a continuity prior, which we think is because we like put this physical information into our model that's not in the continuity prior. But you know, I'm not totally sure like what, you know, how to exactly answer that, but I can think about it.
Okay, let's thank Jenny again.